Hello, everybody. So I'm Pierre Donabouillu from Czech Technical University. It's a joint work with Northeastern University. So I'm going to speak about a tool we've developed, signatr, a data-driven fuzzing tool for R. So what is R? So R, it's not a language designed by computer scientists for computer scientists. It's a DSL for statisticians, which also designed by statisticians. And actually, one of the creators of R, George Ross Ihaka, was a professor of statistics here at the University of Auckland. So this is a language that is widely used, actually. It's 11th in the TOB language index, whatever it means. And it's a de facto standard for statisticians. So each time they develop a new statistical method, they will also create a new R package. And so there is a big repository of curated packages for R called CRAN, which we have about now 16,000 packages, and which has been used for over 25 years, which has grown exponentially. And so really the value of this language is the ecosystem. Also, so R has been designed by statisticians, and it's a mixed bag of paradigms. So on one hand, it's a functional and lazy language like Haskell. On the other hand, it has 5 different object-oriented systems. And so it's also a dynamic language, so there is no static type notations. And so the lack of types it hinders the maintenance of large code bases. And so many dynamic languages such as Python or Ruby have added types into their language. And we also have embarked into a journey to add a type system for R. We want to retrofit types into R. And so how to do that? So we could design a type system by hand manually and then try to infer it statically. But R is a very dynamic language. So we had a paper last year at UPSLA about how complex eval is in R. It's one of the most powerful eval you can have in any languages. In R, everything is a function, and you can redefine if, for instance. You can give it a new meaning. And also, it has the philosophy of failing as late as possible, or to continue execution whatever it takes. So another approach is to use dynamic analysis. And so that's what we did 2 years ago. So there was this paper about simple types for R. And for that, they were tracing existing code to find the types. And so this has some limitations, because when you do dynamic analysis, you need to have some code, and you need to have some valid inputs to run the code. And so it gives you an incomplete picture of the behaviors of a dynamic language, or an incomplete picture of the types when you are trying to infer them by tracing. And so our approach is to use blackbox fuzzing to uncover more behaviors. And so what is blackbox fuzzing? For those who don't know, it's when you run your program as a black box with random inputs, and you monitor its behavior. And usually you do that to try to get failures, to try to get bugs. But in our case, we don't want to get bugs, or it will be a byproduct, but we just want to uncover new behaviors, new types, new type signatures. And there are some challenging in fuzzing R functions. So, I mean, there is no static types, I said it, but it's a challenge because you don't really know what kind of arguments to send to a function. And it's also very difficult in R to generate complex values automatically because R lacks structures. You have lists and you have data frames in R, but you don't define them. So data frames are tables with column names, but you don't define them at the beginning. They are dynamically built, so you cannot really generate complex values in R. And so our idea to solve that is to use observed realistic values for fuzzing. And so we are going to record and store R values while we trace some code. And we are going to build a database. So can we, with this approach, find more type signatures than by just tracing existing code? We will see that. And so the approach for first step, we are going to build a database by collecting real R values once, and then we can fuzz many different functions randomly by sampling from database and uncover new behaviors, in our case, uncover new type signatures. So let's look at the pipeline. And so first of all, the recording pipeline, so how to build a database. So we give it a list of R packages, and we extract runnable code from the packages. We get many files that we're going to run, and we are going to record arguments of functions and the return values of the function and store them in some small database that we're going to merge later. And at the end, we're going to get a big database of real R values. So I will detail the steps. First of all, we extract runnable code. Usually in CRAN, so it's curated, and people tend to add tests in the package to have examples for each function, also to have vignettes. So vignettes are large-scale examples where they try to combine several functions and to show a use case. And so we extract that from packages, and then we are going to trace. So we get many files. We run them with a modified R interpreter, in which so you can find it on GitHub. In which you have hooks. And so we use a function exit hook to capture the arguments of the functions and to store and to capture also the return values. And why do we use the exit hook? It's because R is lazy, and so arguments are only in the worst case are only materialized at the end of a function. So it's a tool paper, so there are technical details about the implementation. I don't explain everything, just that the hooks are about 600 lines of C++ code. And of course, it entails a slowdown, so in average, it's 3 times slower to trace, to run this code, and the worst case, it's 8 times slower. So this is for the tracer, and so we store the values into a database. And so we decided not to reuse SQLite, for instance, but to build our own database. Why is that? Because we wanted really a database for the specific R values, in which that would be specialized for data frames for this kind of values that we have in R, and also to have a query API that would be easy to use to randomly sample from it. So we store only unique values in this database. There are some implementation tricks to make it store so that it's not too large, because we're going to store millions of values. And the query API supports randomly sampling depending on the type, on the class, on the dimensions, because R has vectors. And it's about 5,000 lines of C++ and 1,500 lines of R. And then, so we are going to use these values we have stored in the database to fuzz R functions. So the algorithm is quite simple. We first seed a call by using known values that work for the function if we have tests for the function. And then we are going to get the most general value that we can give to the parameter. So we call that relaxing. We relax on all possible parameters, on all the metadata we have. And then we are going to generate a new call with that. And then we are going to get more and more specific values and generate call with that. And so a call is successful if we get no warning, no errors, or no crashes of the R interpreter. And we are going to store both the bad calls with the error messages and the successful calls with the arguments and the return values. And so it's a bit similar in spirit to mutation-based fuzzing. We are not mutating values, but we are choosing values based on previously valid values. And so now the fuzzing pipeline and how we generate the type signatures. So we give it a list of R functions, and we have this big database of R values. And then in parallel, we are going to run to throw random values using this algorithm I just presented to the functions. And then we capture the calls. We store the successful calls, and then we can just infer the signatures by looking at which arguments worked and which return value worked. And so we did that on 2 big servers, because there is we are going to run a lot of values to the functions. So 2 Ubuntu servers, each with 72 cores, about a quarter of terabyte of RAM. So to give now some numbers, we recorded 652 packages to create the database with about 389,000 lines of code. We got about 40 million unique values, about 38 functions. And it took 16 hours to generate the database on these 2 big servers. And it took only about 300 gigabytes of disk space. So we had that big database, and then we decided to fuzz about 5,000 functions from 100 packages. We do that in parallel, and then, so what's interesting is that we generated 24 million calls, but only 14% were successful. And at the end, we get about 3.3 million traces for 2,300 functions, so it's about half of the functions. So to look a bit at the results in more details, so we get call signatures for 45% of the functions, compared to the approach with just running the existing code. We uncovered more functions with type signatures. And so if you look on the graph on the right, it's a log axis. Each bar represents a function, one function, and the length of the bar is the number of type signatures we uncover. And so you see that with fuzzing, we uncover many more type signatures. But sometimes we don't find any type signatures. And why is that? It's because our fuzzing strategy is still a bit simplistic, and we ignore dependency between arguments in the function. Some arguments can look into a data frame and so give a name inside. So we don't have a very sophisticated strategy to generate arguments. So to conclude, so we have used fuzzing to get insights about code, not only to find bugs, although we actually found bugs also during that, and we reported them. So we used a database of observed value to fuzz dynamic languages where it's complicated to generate complex values. We uncovered many new call signatures for R functions, and so it's a step on our journey to build a type system for R. And so we see this tool as a way to explore the expressiveness of a type system. And if we get many type signatures for one function, maybe the type system is not expressive enough. So we can compare different type systems with that. So it's a tool in a data-driven language evolution toolbox. So the tool is available. We had an artifact that is reusable. And so about the tool itself, our next goal is to improve the precision of the fuzzer, and so to get a better success rate of than 15%. Thank you.
Any questions?
Yeah.
Thanks. Sorry. You said which R's worked and which functions were successful. Could you clarify what it means that it worked?
About functions?
As I understood it, you fuzzed a function and you'd feed an input into it. And if the function happened to have error handling and check for a type it didn't expect, it might, complete without an exception or anything, right? So I'm asking, you passed an argument to the function and the function worked. What did it mean that it worked?
So I don't remember exactly when I said the work, but when it's successful, it means that there is no warning or no errors, or that the R doesn't crash.
Okay.
So I don't remember in which context I said it work.
Okay, but successful means that it didn't explicitly issue a warning.
Yeah, or an error, or the interpreter, the R interpreter doesn't crash.
Okay, but it might still not be necessarily the type that the developers were expecting.
Exactly. So that's a very good point. So it's garbage in, garbage out sometimes.
Yeah,
so
okay.
For instance, you have some functions to compute registers, and so you should give them strings. But if you give it a Boolean, it will cast the Boolean to a string, and then it will still work. So now you have coercions into any values, nearly any values. So yeah, there is this problem how to evaluate if the function it does actually what the developers wanted. Yeah. But we don't have an oracle that we could develop some heuristics.
Okay, so my second question I think is related to that, which is does R have duck typing? That means that you might wind up with these complex union types that you have to infer.
Yeah. You mean the signatures?
I mean duck typing like in Python, like if it looks like a duck or it quacks like a duck. So a function that adds its arguments together, where the add might apply to an integer as well as it applies to a matrix, and so you you wind up having to.
Yeah, but designing type system for that means that you could have the union of everything you give to the function, but it makes big type signatures, and so.
But that's something you have to deal with for your type
Yeah.
system for R.
Also something that is changing in R is that all these object systems, and it has especially an object system based on generics, on generic functions, like in command list.
Okay.
So yeah. So
Thank you.
that are things we are trying to explore to have a better type system for sure.
Interesting work. I'm curious, when you say you've uncovered many new call signatures for R functions. I mean, I haven't used much R, so I've used Python. And often what happens is you have functions that take either a scalar input, in which case their output is also scalar, or they'll take like a vector input and their output is kind of a map and produces a vector. So there's this kind of relationship between the input and output that you could maybe observe in the data. It's sort of like the arity of the input has some relationship to the arity of the output. Do you do any kind of like abstraction over the observed signatures, or do you just kind of list them all?
I list them all. So like in this tool, the goal is to list all the type signatures for each of the core.
Okay.
So you have a bag of all the type signatures, and then so in this paper 2 years ago, they were unified somehow. So they were mainly by just having the union, for instance, of the various input types. Yeah.
Okay.
But yeah, we're also thinking of how to have maybe a different type system when you could have the length of if it's scalar or no scalar, or the length of the vectors you give to R.
Right. Yeah.
Yeah.
Thanks.
Okay, let's thank the speaker again.